Aloha, Fide, and aloha. Thank you all for joining us today. Welcome to the second webinar in the Pacific Desk 2023 webinar series. I am David Hitzel, the Pacific Desk Guam instructor, and today's topic of discussion is nascent technologies in the tsunami warning business. Usual reminders before we begin: this is being recorded for educational and documentational purposes and is posted simultaneously on Facebook Live. Please leave questions in the comment section, including your location and affiliation. You can also ask questions through Facebook Live, or at the end of the talk, you're free to ask questions orally. But we ask that please do not have your audio or videos switched on at any other time. And then lastly, I will be posting the video as usual to YouTube, and it'll also be on our Facebook page. Okay, upcoming webinars. Our next webinar in late August will provide an overview of wildfire across the Pacific and current efforts, programs, science, and informational resources to mitigate it. Current opportunities in wildfire science, including participating in the PIA Wildfire Network, will also be discussed. Our speaker for the webinar, this webinar, will be Elizabeth Pickett, the co-executive director of the Hawaii Wildfire Management Organization. And then for later on in the year, I recently visited Japan, and I took the bullet train, the Shinkansen, and I had asked a friend of mine, in a place that has so many earthquakes, how do they manage having a train that goes 180 miles per hour safely? So he educated me that the Japan has what's called the earthquake early warning system, or Kinkyu Jishin Sokuho. And in this way, the Japan Meteorological Agency provides residents in Japan with earthquake early warnings. This system has been in operation since 2007 and issues alerts just as earthquake starts based on the P wave, and provides valuable seconds for people to protect themselves before the strongest shaking arrives. Not only do alerts come over the TV and radio, but the system slows trains and stops elevators before damage may occur. Like I said, in Japan, this is the Kinkyu Jishin Sokuho, but they also, in the western part of the US, have something called the Shake Alert. So I'll be arranging a webinar on that topic, hopefully for September, October. Okay, and today's panel is Dr. Andrei Natarov. He is a duty scientist and oceanographer with the Pacific Tsunami Warning Center. Before joining the PTWC in January 2021, he conducted research at the International Pacific Research Center at the University of Hawaii, where he studied ocean waves, currents, their instability, wave breaking, and mixing. Andrei received his PhD in physical oceanography and scientific computing from the University of Michigan. Okay, so what spawned the idea for this talk? Way back in 2015, when I began working for the Pacific Desk, I was in our conference room, and I saw over on the wall this elaborate poster of a cable network connecting everything around the world. And I was ashamed to admit that I didn't know that this, at least how extensive, I didn't know how extensive this cable network was. I knew, I guess, in the back of my mind somewhere that something like this may exist. I'd once been told that a great-grandfather worked on the undersea telegraph line between Los Angeles and Catalina back in the 1920s. But I guess I had no idea of the extent of the various connections that were in existence today. And I think, like a lot of other people, I just take for granted that this kind of infrastructure exists. And that may be partly due to the fact that this system and the servers it's connected to are referred to as the cloud, as though it's some sort of ether. But as of early 2023, there are 500 of these submarine cables worldwide capable of carrying information at speeds over 200 terabytes per second. Modern cables are not much bigger than a garden hose and use fiber optic technology, a series of thin glass fibers through which information travels at close to the speed of light. Glass fibers are insulated in layers of plastic and steel for protection. But because they're relatively vulnerable, there's a lot of redundancy with multiple cables placed along well-traveled routes. Initially, the cable systems were built and owned by telecom carriers, but as of the last decade, they are now mostly constructed and maintained by companies Google, Facebook, Microsoft, and Amazon. And especially in the latter case there, the cables can use the modern-day trade routes. So I'm hoping to do in the future webinar specifically communications-based webinar specifically on this topic, because there's a whole host of political, cultural, economic, as well as scientific implications involved here. So what does that have to do with the webinar today? Well, there's a plan to literally piggyback on this existing infrastructure and put tsunami sensors and other scientific sensors as well. So this plan is known as the SMART, or Science Monitoring and Reliable Telecommunications Cables Initiative. SMART cables would increase the existing number of deep ocean pressure sensors to several hundreds, greatly improving the accuracy of warnings, as well as increasing the time to warning and the potential for false alarms. So this and other topics of early warning systems for tsunamis is the topic of discussion today. So with that, I will turn it over to Andrei.
Okay, thank you, David. Can you see my screen now, or should I share it again?
Let me stop sharing.
Oh.
Or maybe, no, there we go. Should be able to.
Okay. All right. Thank you for coming to the talk. David described pretty well already a part of what I was going to talk about, but to lead to the necessity of using in any way we can the developing technologies to help tsunami warning kind of prompts me to address things which are very well known to many people, but maybe new to some people, to stress again the importance of tsunami warning system and whether it's possible to improve the capabilities of the tsunami warning system. So my talk the outline of the talk will consist of 4 major V's. So tsunamis, and the damage, the science, the service, and the future. In the damage, I will discuss things that everybody knows pretty well, that destructive tsunamis do a lot of damage. And also we'll talk about things which are not discussed very often. How much does the warning system can improve the picture with the damage? And after that, we'll talk about the science of tsunamis, then the service that is conducted by the tsunami service providers. One of them is the Pacific Tsunami Warning Center. And then we'll have a little bit of time to talk about the future, what is desirable in terms of the new instrumentations and methods of analysis, and what is doable, and whether it's worth doing. So I'll start with the damage, and the first part is the disasters that are recent, past, and future. Recent ones are the easiest to remember, and I'll just start with this century. The deadliest recent disasters are, of course, the 2004 Indian Ocean disaster, which resulted in nearly 230,000 deaths. In blue color, you see the estimates of their earthquake magnitude that occurred during that event. And actually, the very initial magnitude estimate was 8.8. These higher estimates, the community needed time to arrive at a better estimate of the earthquakes. And that's one example where we need a better way to estimate the earthquake magnitudes sooner than several months after the case. So a lesser known Indian Ocean earthquake is the one that followed within a few months on March 28th. After the big event in 2004, there was another Indian Ocean earthquake in a similar location of a slightly smaller magnitude, 8.7. It resulted in only 1,000 deaths on the Indonesian island of Nias. So it was much better in terms of outcome. I will get back to this when I discuss the other sort of damage due to tsunamis, and that's the damage due to unnecessary evacuation in just a few minutes. So another example is the 2010 earthquake in Maui and the tsunami, which resulted in 156 deaths. And I think the last one I'll mention is the big Tohoku tsunami, the earthquake of magnitude 9.1, which resulted in 18,000 deaths. An argument I've heard many people make is that because Japan has such an advanced tsunami warning system, that greatly reduced the number of deaths in Japan. So it's basically, if you compare it to the number of deaths in the Indian Ocean due to an earthquake of a similar magnitude, it's an order of magnitude less. And sometimes we look at the tsunamis, recent ones, and forget that they are quite unpredictable. They can happen in places that we haven't observed a big tsunami at, like in our recent times. So I'm mentioning the Lisbon 1755 earthquake because it does have relevance to the smart cables. The Portuguese government, because of this particular earthquake, was convinced to support the smart cables initiative, and it's one of the first countries that did this, and all because of this very old earthquake, which we have a pretty rough estimate. It's in the range between 7.7 and 9.0, but we do know that it resulted in 60,000 deaths. Another historic event, which has a lot of significance, is the 1700 Cascadia earthquake. We know that tsunami occurred due to records in Japan. So in Japan, the waves that were experienced are consistent with the earthquake of magnitude between 8.7 and 9.2 in Cascadia. I couldn't find any estimates of the death toll of this earthquake, but I read that some of the villages in Japan were destroyed. I don't know what kind of population damage it was in North America at that time due to this event. And the future, a study done by University of Oregon or Oregon State University, probably, scientists suggest that there is a 37% chance, more than 1 in 3, of a magnitude 8.2 earthquake in the Cascadia region again before 2060. So in the next 50 years, the study was conducted in 2010. They said in the next 50 years, there is a very good chance of a very strong earthquake again. And we know, based on research done on 1700s Cascadia earthquake, that this will result in a devastating inundation of the cities in the Northwest. So another type of damage is unnecessary warnings, and there are several examples from recent history. So there's 8.2 earthquake in 2017 in Mexico, 2018 Kodiak Island, Alaska, and the earthquake that I have already mentioned, lesser known Indian Ocean earthquake, which, although it did take lives of 1,000 people on an island of Nias, however, did not result in a significant devastating tsunami in places like Thailand, Sri Lanka, or Indonesia. And these places, because it was so close in time to the first earthquake, evacuated, but it appears that there was no necessity for that. So the Pacific Tsunami Warning Center would still issue not evacuation, we call it a threat message for international territories for earthquakes which occur close to the coast of such magnitude. And that's because we simply do not have time to wait for a better estimate of the fault parameters, etc. So places like this will be placed in a warning or equivalent of that based on magnitude alone. But wouldn't it be nice, actually, at some point to have a capacity to know whether a huge magnitude earthquake will result in inundation or not? So we will discuss whether it's possible or not. There is some hope that it may be possible with the use of cabled networks of bottom pressure sensors and seismometers. So the conclusion is very simple here. If you phrase it based on how I defined the damage, is improvements in tsunami forecasting, and the improvements would be the timeliness, the accuracy, and the reduced uncertainty in them would significantly reduce damages. So damages themselves would be reduced, first of all, because of fewer unnecessary warnings, and of course, due to evacuations that will be more effective. So is it possible to improve tsunami forecasts? To address this question, we will go a little deeper into the science of tsunami. Some of this material is elementary, but it's always nice to revisit elementary material to know, to see what the possible improvements are. So I'll start the science of tsunami with how we experience tsunamis normally. We experience them is an inundation, and for an inundation of coastal areas to occur, you have to have displaced a large volume of water. Here I put the word sudden in the definition because, I mean, we can displace a large volume of water not suddenly, but the hurricanes can carry a lot of water on shore, which would also result in inundation. But for tsunamis, we're really interested in sudden, meaning on the time scale of minutes or tens of minutes, very fast. And if you think of processes capable of inducing a sudden displacement of a larger volume of water, there are many things you can consider. Well, if you thought earthquakes, then it's not quite directly relevant. So the first part is that seafloor deformation needs to happen for the sudden displacement of a large volume of water to occur. And that can be brought about by the rupture of the solid earth. So I'm not mentioning earthquakes yet because earthquakes are really just it's not the process that does the seafloor deformation or it displaces large volume of water. Earthquake is responsible for seismic waves that we use to infer the parameters of the rupture. So here's a nice illustration I took out of some recent paper, which kind of, unlike other pictures of earthquakes, I think shows a little bit more than what is usually shown, that it's a kind of a limited region. The displacement is non-uniform across it. It happens under loading stress. So there is a kind of a rupture region. It has parameters. It's characterized by the strength of the material. But what I like here is that it's a kind of a limited extent, and you can see that the size of the displacement and the horizontal extent of it, and they kind of related in this way. And this is how it's normally represented. Like people use an approximation of certain fault plane along which the slip or separation, the displacement of solid earth takes place. And you can see there's a lot of parameters that I needed to really describe the rupture in detail. So there is this angle at which the slip occurs, there is orientation, the strike angle, and there is a mount by which this slip occurs. And here you show, the diagram shows seismic waves in the form of this concentric sort of, in this case, cylinders propagating away from the focus. And the epicenter is the basically geographic location of the focus. So the parameters that characterize the rupture would be the focus, which consists of epicenter and the depth, and all these angles along which the slip occurs, by what amount, and along which geographic direction. Seismometers are devices that measure and record the seismic waves, and those then can be used to infer the parameters of the rupture. I have to say tsunami warning centers in the initial first few minutes can only estimate location, depth, and magnitude of the earthquake, not other parameters. And that's what kind of limits a little bit capacity to issue precise, accurate warnings early. So once the rupture occurs, it displaces the volume of water. That's what, we figured out that that's what's necessary for inundation to occur later. So here in this picture, you can see that kind of a fault movement similar to what I've shown on the previous slide, although in a different direction, displaces the water. And so a few important things to note here is that the entire water column it gets displaced, so the volume is very large. And based on this, you can infer that the deeper the ocean at the place of the earthquake, the more water is displaced. So you could expect a stronger wave, basically, if it occurs in the deeper part of the ocean. And also notice there is a directionality. So the fault orientation determines in which directions the disturbance propagating away from the epicenter of the earthquake will be the strongest. Here you see that along in the directions parallel to the fault, there will be a major emission of a wave energy, whereas in the direction sort of parallel or with a small angle to the direction of the fault, the tsunami may not be as strong as in other directions. And let me remind you that our initial estimate does not contain the orientation of the fault. So therefore, there is uncertainty in the early products issued by tsunami warning centers due to that. So once the initial volume of water is displaced, the disturbance propagates away from the source in the form of waves. Tsunamis is just another form of a surface gravity waves, just like the wind waves, which have the following characteristics. The surface gravity waves, they decay with depth. So the amplitude of the velocity associated with the wave decays with depth. And the scale on which it decays is kind of proportional to the wavelength. And that's where tsunamis are different from the wind waves, because their wavelengths are so large at the location where they have been created that they basically do not decay. The entire water column is moving. So this picture represents a general surface wave. For tsunamis, they would be feeling the bottom, the ocean bottom. So it's much larger amount of water is moving in a tsunami. For long waves, the propagation speed can be calculated, estimated, and it's just proportional to the square root of GH. G is the gravitational acceleration, 9.81 meters per second squared, and H is the depth of the ocean. So you can see based on this formula that the deeper the ocean, the faster the waves propagate. And as the wave enters shallower waters, like in this diagram below, it begins to slow down, first of all. And then, of course, because, it's just like in a traffic jam where you have a traffic slowing down, you have piling up of wave energy density, and that causes the steepening of the waves. So at some point, the wave will slow down so much, the parcel movements within the wave will exceed the propagation speed of the wave, and the waves start breaking eventually. So these are important considerations for how we use DART buoy data in tsunami forecasting. In deep water, the wave behaves very much linearly, meaning that the terms like this in this equation, which are due to basically, we call them nonlinearities. So are small in the deep ocean. In the shallow water, first of all, the amplitude of the wave becomes large, and second, the wavelength for which this spatial derivative is responsible becomes smaller. So it's a double whammy for the nonlinearity, and the wave becomes nonlinear and unpredictable. It's much more challenging to invert this if you want to correct for the source. If you measured a nonlinear wave somewhere to figure out how it's related to the magnitude of the earthquake, is a much more challenging problem than doing it for a linear wave, which is basically proportional to the amount of energy which is released in an earthquake. That's why the most useful bottom pressure sensors would be for tsunami prediction and for tsunami detection, and data assimilation would need to be placed in the deep water. Right, so much easier to assimilate into a forecast. So that's it for the science part. Now, the service provided by the Tsunami Warning Centers is based on the network of sensors. So here, what is shown in the upper plot here is the seismic stations, or the seismometers around the globe. So basically, we receive seismic data from these devices and process them. And if we get a signal that there is a very large disturbance on several of these seismometers, then a duty scientist gets alerted, and they come to the operations room and start processing, looking at the seismic data. The lower figure shows the sea level stations. So basically, the core of our observations, the seismic network and the sea level stations. There's two types of sea level stations that we use. One of them is coastal tide gauges. So in this plot, they're shown in like small little circles. There's a lot more of them than the larger circles. And the large circles represent the so-called DART buoys. DART stands for Deep Ocean Assessment and Reporting of Tsunamis, but these are basically deep ocean bottom sensor recorders, bottom pressure recorders. So these are the ones that are very useful for inversion and detection of tsunamis. But almost every time we do have a tsunami, it first gets registered at a it's a tide gauge station at the coast. First of all, there's more of them. They are, in some places, they are very dense. Unfortunately, these data can only be used for detecting tsunamis and measuring how big they are, but not for improving the forecast very much. Not in a systematically automatic way, anyways, not yet. So here's a system overview of DART buoy. You have a bottom pressure sensor. And it is connected. It communicates with the surface buoy through acoustic transducers. So because you cannot propagate electromagnetic signal in seawater, they communicate through acoustic signals, the surface buoy and the bottom pressure recorder. So that immediately puts some limitations on the bandwidth and how much data can be transmitted. Another serious problem, of course, is that because these are isolated, the battery, the power supply issues are very important. And that's why under normal regime, the data is pretty sparse in time, not particularly useful. But these DART systems get triggered when there is a fast increase in the signal. Then the power supply gets, basically the data stream gets activated, and they start supplying data at a much higher rate. The right panel here shows the kind of DART buoys that were deployed initially. You can see there's several countries participated in this program, the US, NDBC, National Data Buoy Center. Not all of them are functional at this point, but so one problem with them is, of course, the maintenance is very expensive, and many of them have gone out of order and have never been repaired. But they provide a very useful set of data for tsunami warning centers. So first of all, notice that how they're positioned. They are positioned close to the ring of fire, so to speak, where the large megathrust earthquakes occur, but not too close, because you don't want to mix so they register the signal due to the earthquake itself, because of the shaking of the seafloor. They also experience accelerations and register them in their data, so they can get triggered by the earthquakes. But you want a cleaner signal from cleaner separation between the seismic signal and the tsunami signal, which would come a little bit later. So they are placed a little distance further away from where you expect the epicenter of the earthquake to be, and that introduces another delay in detecting tsunamis. So now I will summarize the service provided by the tsunami warning centers. So we communicate with our partners and the public through message products. So basically, when we detect an earthquake which is sufficient for us to address it, it doesn't necessarily mean it's a threat or anything. Disseminating no threat products is probably more important than threat products, because people would not, it kind of guarantees that there's nothing to worry about. So, but the initial message products are based on the earthquake location, magnitude, and depth alone. As I mentioned, we don't have an estimate of the fault parameters 8 minutes into the event. So there are the following type of international message products. So PTWC has international responsibilities and also has domestic responsibilities. I'll start with international ones. So we issue a tsunami information statement, or TIS, no threat in most cases. It's simply to inform people that even though there was a strong earthquake, there is no tsunami threat. And then there could be a tsunami information statement with a potential threat. So when it's not clear whether the threat, the tsunami has actually been generated, but there is a good chance. And then we'll have to wait for confirmation from the sea level stations whether there is anything measurable or threatening. And also in the meantime, we will run our forecast models to see whether they anticipate any threat to be there. And finally, if the earthquake is strong enough, then we issue a threat message. So for international products, we do not issue things such as warnings and watches, because these trigger evacuations, and we cannot be doing this for international products. For domestic territories, which for us include the state of Hawaii, Guam, American Samoa, and Puerto Rico and Virgin Islands, there is a different set of products. The first one is similar to the TIS no threat, where there is a sizable earthquake, and but there is no threat, and we can be more or less sure that that's the case. Then there's a tsunami watch, which is normally issued if there is a threat, and it's less than 6 hours to the territory that we are placing in the watch. The final product listed here is a tsunami warning, but that would trigger evacuations. But sometimes evacuations are unnecessary, yet sizable tsunami is expected between 30 centimeters and 1 meter. In that case, we issue a so-called advisory. It just advises people not to be near the ocean, but does not really require evacuation. One of the advisories that we've issued was last year in January 20, I think it was 15th. It was the tsunami advisory for the state of Hawaii because of the volcanic explosion in Tonga. But afterwards, we received some notification that there was some property damage to the boats in some places, yet it was justifiable not to put the whole state in the warning. So I've described how we use dart buoys to improve forecasts as more data is coming in, and finally, if the tsunami does reach the dark buoy, then we can refine the rupture estimates of the earthquake and make a better forecast based on observations. But dark buoys are kind of isolated, and I listed the problems that they have. First of all, that they communicate via acoustic signal with the surface buoy. So it seems like an obvious improvement over darts. It would be some cabled bottom pressure network of a cabled bottom pressure sensors. So one obvious advantage, if it's a cable, then there could be a constant stream of data in real time. Real time meaning here is very high time resolution. So unlike dark buoys, which are most of the time are dormant and only get triggered during the event, here we could just receive the stream of data all the time because they're connected electronically. A continuous supply of energy, another reason to keep this stream of data coming without breaks. No need for surface buoys. Surface buoys get vandalized by accidents or by not very well-meaning people, and that's a big problem for them. You can create a high-density network of instruments, and that would give you like a more or less like a spatial picture of what's going on. You can estimate not just the wave amplitudes, but also wavelengths and things like that of a wave. Sensors have high reliability, and also regional versions of such cabled bottom pressure sensors have been implemented predominantly in Japan, but Canada and US have smaller versions, and tsunami warning centers use some of that real-time sea level stations to supplement their sea level network. But what's the disadvantage? There's only one that I could find in literature, and that's high capital cost. The initial investment into this is very high, even though it is mentioned that probably over a lifetime, a network like this would be cheaper than the alternatives. Dark buoys require a lot of attention and maintenance if the effectiveness of a network is to be maintained. Other alternatives are like seaboard measurements are also quite expensive. And based on this alone, it is projected that a tsunami dedicated cabled bottom pressure sensors network is not going to come into existence. Fortunately, there is this smart cables initiative, which probably was triggered by, well, I mean, when I said will not come into existence on a global scale. So, for example, PTWC needs to be able to forecast tsunamis all over the Pacific and even in the Atlantic Ocean. So sure, you can build small networks around Japan or like in small locations, but the global one will be too expensive according to the literature. David showed this picture in the beginning of the presentation. So this shows telecommunications cables. These are not smart cables. These are existing ones, and they're shown like it's at what time they were laid there. Like, so you can see like the green scale here. So the green earth is the older the telecommunication cable, and the white cables here are still not, well, are in production, I guess. So these do not contain any sensors that the tsunami community or oceanographic community in general wants companies that lay cables to incorporate into them. But it's a very strong proposal, which is welcomed by many of them. One reason for that is also because these sensors would help monitor the environment in which the cables are placed, so that would help maintenance of the cables themselves. Other things shown in this figure are the earthquakes. So the red colored circles of different diameter are the earthquakes in magnitude between 5 and 9. And every 300 kilometers, there is a repeater on this cable. So So the idea is actually to incorporate these sensors into cables shown in white here. And also when they replace older cables, like Portugal is planning to do, because they will be replacing some older cables between Portugal and Azores Islands. They may incorporate now the sensors that would be useful in detecting tsunamis, bottom pressure sensors and accelerometers. So this figure shows what kind of a sort of a system overview. So in the housing, which can sustain pressure, you would place accelerometers, pressure sensors, and for other oceanographic applications, it would be temperature sensors, because this could be also used for things other than tsunami warning. So that's pretty much it. And when I said nascent technologies, it means it's not yet ready, but there is a well-supported initiative to do that. The other two things that I did not have time to prepare anything about, but need to be mentioned because they're even like maybe even further into the future, are extracting information about tsunamis from traveling ionospheric disturbances and hydrophones. Well, I'll just say one word about the ionospheric disturbances. The last year's Tonga eruption produced a very strong atmospheric waves, but also turns out that which in turn actually generated a tsunami wave, but it couldn't work the other way around. Tsunami generated by an earthquake can produce sizable ionospheric disturbances, which, if detected, could be used to estimate the parameters of the tsunami. One problem with ionosphere that even though it's very sensitive to even things like, just slight sea level elevation, it's also sensitive to all other things. So to separate tsunami signal from all other signals that leave their signature in the ionosphere, a lot more research needs to be done before this technology can become operational. I think I'll finish my presentation at this point. Thank you.
Thank you, Andrei. I'll open it to questions from anybody else. If they want to, I have one question, but if you'd like to ask a question, you can go ahead and unmute yourself. Or you can ask through the chat, that's fine too. Okay. Okay, maybe, so my question was, maybe I'm asking for top secret information here, but has there ever been a incorrect no threat message? You mentioned at the beginning of the talk that one of the biggest concerns was preventing unnecessary evacuations, because evacuations in themselves can be problematic. I think you're thinking partly of Oahu because of the large population, but other areas have large populations. So has there ever been an incorrect no threat message? And
yes, there have been. I don't remember the details, that may have been before my time, but I have heard from the emergency managers in Hawaii, and it wasn't so bad because initially there was a no threat message which had to be upgraded to a threat later. So, but it still makes people nervous. Yeah, it has been the case. Fortunately, the no threat message with big consequences, I cannot remember. There were initial mistakes later corrected, but not maybe you can argue that in some cases we put places in warning a little too late. For example, when there was a volcanic explosion in Tonga, the American Samoa placed themselves in the warning before we did. So that's but we did it within minutes afterwards. But that would be a better way to deal with this, just to place them immediately into warning. So there have been cases, but without huge consequences so far.
Okay.
They indicate the need to improve forecasting for sure. Yeah.
Okay, and then I guess that would be the second part of my question. So are there areas of the ocean that you are not as well, can't see as well? Not necessarily blind, but not.
Oh yeah. Yeah.
Well,
so there are areas of the ocean which are, obviously we don't have any sea level measurements stations in the open ocean. There's like dart buoys are not everywhere. In some places you don't even get coastal tide gauges, and in many places you don't even have seismometers. The seismic networks are very sparse, and you have to wait quite a bit of time before you even begin to process an earthquake. So in August of 2021, there was an earthquake in the region of South Sandwich Islands in South Atlantic, and it was very hard to estimate. It was a complex seismic event. People took several months to arrive at the conclusion that it was actually a combination of 3 earthquakes, each of which was stronger than 7.5 in magnitude. But we had some problem with that, and what helped resolve it is the fact that we did get some sea level measurements which showed that our initial estimate was off, of the earthquake magnitude was off. And second, there's very little, not many populated areas around that region. So there was did not pose serious threat to populated areas. Yeah.
Okay.
So there are poorly covered areas in the ocean where we not only in terms of sea level measurements, but even an earthquake could take longer than we want. With sea level measurements, most of the ocean is poorly covered because we have to wait for confirmation of a tsunami hours, even if it's a known area where tsunamis are produced all the time, because it takes a while to get to to the coastal locations.
Okay. Yeah, I wasn't quite clear on, so the smart cables would actually clear up, would provide you surface estimates quickly, or just?
Well, they will. So because they have both, seismometers, so accelerometers, which can be used to measure earthquakes, and pressure sensors. Pressure sensors is all you need to estimate the sea level height.
Okay.
So because tsunamis, the elevation due to tsunami is felt at the bottom, elevations due to other waves is not. It does not penetrate deep enough. So one of my slides was about that, how it's nice to have a pressure sensor at the bottom because it basically only feels tsunamis out of all surface phenomena.
Okay. If anybody else has a question, I want to give them time. I checked on the Facebook side. Okay, then I guess unless you have any other comments you'd like to make, or I think we'll wrap it up there. I really appreciate this talk. I think it's a really interesting subject, and I'm glad to see that there's plans like this in the works, because it makes a lot of sense to, if they're going to lay new cables, that they put the sensors on there, and then that benefits not only scientists and the public, but it also should benefit the cable infrastructure in itself. So.
Right, it's like a synergistic effort on the part of many different stakeholders.
Right.
But one thing I wanted to notice that is, the talk of dedicated networks for cabled networks for just tsunami detection has been there before the smart cables initiative, and also does not seem to be necessarily dead. it's still I think it's a viable option, basically.
Mm-hmm. Okay. Well, my personal opinion is you guys are doing a great job so far. I've never personally read of an incorrect threat message. So, so I've been pleased with the Pacific Tsunami Warning Center products as they are. But it's good to see that there's these new technologies coming out. Okay.
Yeah, thank you.
With that, I will wrap it up for today. And the next webinar will be in late August and pertaining to wildfire. Okay, see you then.